So the length of the orange line actually is going through the Earth's atmosphere exactly. So the longer the line, the more the Earth's atmosphere that little bit of sun needs to go through. So the smaller the angle up here, okay, you can see then that it goes through more of the Earth's atmosphere, significant beam depletion occurs. So what time of year is this? Does it say? What do you think? Winter, very good. Winter for us. What month is winter solstice? December, yeah. And day is 21st, 22nd. I don't know, 21st, 22nd. December 21st, 22nd, the winter solstice for us. Very good. Okay. So I have Monday up here, so this must be kind of where we're ready to start. So the amount of sunlight a location gets is what we call it the insolation. Okay, not like insulation, that pink itchy stuff that you put in your house walls, okay? But insolation, we'll talk more about energy coming from the sun, but is the amount of sunlight that you're going to get. And that could vary because of angle, that could vary because of the number of daylight hours, okay? So actually, to kind of summarize what we've been talking about, we'll talk just a little more about daylight hours. That little video we watched on Friday, I think, did a good job about daylight hours. Okay, but it's all about angle. Of course, we said that the angle throughout the day varies. The sun makes with the horizon. Okay, but as the Earth goes around the sun, we've definitely got angle issues going on. The equinoxes. Go ahead and pick on. What's this? The sun. The sun? Very good. Okay. And what's that star? What star is that?
Polaris.
It is Polaris. Okay. So my tilted axis of rotation is doing that sort of thing. Okay. So this would be, what month is this for us?
January.
Well, could be January, but if it's a solstice, it would be,
Fall or spring. So.
okay, if I'm like here.
December.
It is December. Yep, that's what I was after. December. 3 months later, March. 3 months later,
Oh, yeah.
June.
June.
3 months later,
September.
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 Oh, very good. Okay, cool. Where was I going? Oh, what I was gonna try to ask you is, okay, so here, this you told me was spring, right? March. Who's getting the direct sunlight? Which latitude? Is it the equator, or is it the Tropic of Cancer or Tropic of Capricorn? The equator's getting the direct light, exactly. 6 months later, it's the equator getting the direct sunlight. So in case you want to, this almost reminds me of a MacGyver sort of thing, I don't know. But in case you ever want to go ahead and calculate the angle that the sun should be making at your location at noon, this kind of talks you through it. I'm not going to have one of these on the test. It's just an example from your textbook, and I thought it was kind of neat. So, for instance, this looks like the same globe as you guys told me. This is probably December 21st, 22nd. This is the winter solstice for us. Okay? So the location getting the most direct light is the tropic down there, Tropic of Capricorn. Okay? So you need to know that in order to know what angle the sun's going to make at noon at your location. So the first step is to basically say, how far away are you from, and I'm going to call that later as the subsolar point. So basically you take 23.5 degrees to get to the equator, and then we're about, well, this location of interest is 40, which is about us. So 23 plus 40 is 63. Yeah, 63 and a half. And then you're almost done. One last little subtraction then is to take 90 minus that distance in degrees. So 90 minus 63 and a half is 26 and a half. So at noon on that day, that's how high the sun's going to get at that latitude. So again, it kind of reminds me.
Which is right now.
What's that?
Which is right now. Right. Well, about noon, because we're at the 40th parallel or so.
Yeah, not bad. But we're past the, it's getting higher and higher now since we're past the solstice. So days are getting longer and the sun's getting higher, and it's wonderful. Okay, so this is actually the video that we watched Friday This just kind of reconfirms this. So this would be our winter solstice, okay? One of the things I had you guys do, and I gave you that handout, is, did I give you a handout of the Tropic of, the Tropic of Cancer, Tropic of Capricorn, then you had the Arctic Circle and the Antarctic Circle. So that's 66.5 degrees. Here's the deal.
Is it this one?
Yes, it's that one. Thanks, Ashley. Actually, up here at this line, as the Earth spins, okay, basically that little nugget up there to the north of the, what's the name of that latitude?
Or above, or that one?
Arctic Circle.
Arctic Circle.
North of the Arctic Circle, on December 21st, 22nd, as the Earth spins, no daylight. I know.
But plenty of vampires.
The plenty of vampires, exactly. 6 months later, from December to June, okay, this is our, what solstice is this? Well, summer solstice, exactly. If you put summer solstice, that's probably what I would put too. So how many, well, you already see, how many hours of daylight do you have above the Arctic Circle? 24 hours of daylight, yeah.
I think I'd rather have the darkness than the daylight. You know what I mean?
You'd rather have the darkness than the
I think
daylight.
I'd rather have 24 hours of darkness than 24 hours of daylight.
Yeah, I could see that.
You
So-
know where your circadian rhythms will get messed up?
Yeah, I think it would play havoc with your rhythms. So this is both of the equinoxes. Okay, everybody gets 12 hours of daylight. So here's a figure from your textbook, and don't blame me when I show you, point you out something very problematic in the second column, as some of you already have your textbook open. But what this does is look at hours of daylight by latitude. So remember that 0 latitude is what?
Pole.
Nope.
Oh.
Equator.
Equator, yep. And 90 degrees latitude is the pole, exactly. Okay, so this column's just fine. It says whichever hemisphere, the northern or the southern hemisphere you're talking about, if it's winter, if it's December, if it's winter for that particular hemisphere, if you are north of, what did I say, 66.5 degrees, yep, right here. I don't know why they didn't put that in there. 66.5 degrees, okay? You can see that basically you don't have any sunlight. Okay, I'm cool with that. So notice I blocked out the last 4. Okay, so I'm cool with this one. If it's summer in your hemisphere, then the farther you go towards the pole, okay, the more hours of daylight you're going to get. And actually the Arctic Circle or the Antarctic Circle is kind of that sweet point again. But I have a problem with this. Okay? Basically they're saying the number of daylight hours you get, 2 months, 4 months, and 6 months. I have no idea how that got past their editing. Instead, if you want to go ahead and cross that out and write 24 hours of daylight, starting with actually 66.5 degrees latitude going towards the poles. Here, 70 degrees latitude is all we can do. So 70, 80, 90 degrees latitude. As the Earth spins, you're going to have daylight. Which, I agree, it's almost like I'd rather spice it up with, yeah, the whole daylight. I don't think I'd like that.
Kind of a night owl anyway, so.
Yeah. The last column talks about the equinoxes. Whether it's the spring or the fall equinox, regardless of what latitude you are from the equator, 12 hours. So, I mean, to me, a thing that's striking is, you know, if you live near the pole, you know, towards the pole side of one of the circles, you know, look at the extremes that you go. Within 12 months, basically you go from no sun to 24 hours of daylight. You know, I just think.
Is there no, I mean, there's no real in between then, except then.
It's just great, you know, and I don't even know if it's linear necessarily, but you figure within 6 months it's got to do that swing. So, yeah. We don't have quite that swing. So I put this together, and it picks on, for most of the case, basically, our hemisphere. And some of the times I'll go ahead and try to test you on these general dates, okay? So we've been talking about when the solstices are and when the equinoxes are. Subpolar point just simply means which latitude is getting the 90 degrees, okay? So I went ahead and said, for the northern hemisphere, in the winter solstice, that Tropic of Capricorn's getting the 23.5, at 23.5 degrees down there, they're getting the straight, the most intense sun. At both equinoxes, the place getting the most intense sun, equator.
Right.
And during our summer solstice, who gets the most intense sun, it's 23.5 degrees north, which is the Tropic of Cancer. Okay, then this is very similar to what we had on the previous slide. It just says that, again, the Arctic Circle, just in the northern hemisphere, vampires would flock there in the winter solstice. Yeah, they would leave there definitely as the days started getting longer, approaching the summer solstice. Okay, so it's just something else I put together. Okay. This is a pretty photo showing the sun at different positions, okay? Instead of the sun setting, they're just simply showing the sun kind of dipping down, okay, midnight, and then going back up again after midnight.
That would drive me insane.
Seriously.
Yeah, they'd be like, oh, how do you, yeah, we need our
Never
sleep.
get that.
So that's pretty cool.
That picture that's
What's that?
picture is pretty cool.
I think it's pretty cool
Though
too.
I've seen them like suns on the horizon, probably don't fit.
Well, they're separate pictures and then put together.
Right. It's
Yeah.
time lapse.
Unless it's one elaborate sun dog.
Right. So this is kind of a difference between astronomical seasons and kind of when it really is the season. There's a delay. Can you see the delay between when actually, for instance, let's pick on, this is like the winter, you know, the axis of rotation tilted like this, the sun's there, this is winter for us. But it says December 21st is when our shortest days are. But actually, there's a lag between when the dead cold times are. And that lag kind of comes from, like, have you ever had a swimming pool? I think I've talked about this before. If you fill a swimming pool with water, it takes a little while for it to heat up, or it takes a little while for the swimming pool to cool down. Okay, that's kind of what's happening here. So, okay. Now, as Monty Python would say, on to something completely different, or something like that. Yeah. Now for something, I don't know how we use it. But anyway, okay. So insolation is the amount of energy a location's getting from the sun. Okay, amount of energy, insolation. So when you kind of talk about sun's energy, you talk about energy when you kind of talk about energy in general. So you might have learned in physics that there's this energy associated with motion. We call that kinetic energy. Okay, and then there's the energy that associated with position, waiting to be unfolded. Exactly, it's called potential energy. So one way we can kind of think of potential energy is just kind of by location of this pen. It has the potential to actually have motion and fall through the air. Okay, so it has potential. So if I go ahead and take its potential energy, turn it into kinetic energy. Okay, it has less potential energy now because it's closer to the floor. Okay, it's converted some of its potential energy to kinetic energy and kind of spent it. So kinetic energy is associated with motion. Potential energy is what we call stored energy. So with regard to energy, we have kind of an assortment of energies. Okay, and actually you might recognize some of these energies we can kind of go back and forth between mechanical and electrical, chemical, electrical, chemical, mechanical, okay, nuclear, electrical. What's that?
I said nuclear and chemical.
Nuclear and chemical? Yeah, exactly. So we can kind of go back and forth between these different forms of energy. The bottom one, electromagnetic radiation. Yes, electromagnetic radiation. We're going to be spending a fair bit of time talking about this. And I'm going to abbreviate it as EM radiation, sometimes just EM. Okay. That's basically kind of summarizes in general what the sun can send us. Okay, the sun really doesn't send us, although it has nuclear reactions going on in its core that ultimately create the energy that we receive. We receive it in the form of electromagnetic radiation. We can convert it to those other things. So really, especially later on in the course when we start to talk about clouds forming and stuff like that, water basically going from a gas to a liquid, it kind of slows down to a solid snowflake. Basically, as I did that, to a liquid, to a solid. Basically, that's kind of showing how much kinetic energy that those things have. But all matter, whether it's a gas or whether it's a solid, all matter has motion, okay? So this actually is kind of showing you cute little water particles, kind of their little motion. They are adorable. They have vibrational motion, okay? Kind of if I'm the oxygen and I have hydrogens on each one of my vibrational motion, okay? They have rotational motion, okay? And not up there is my favorite. Go ahead and put this whole thing up there. Translational motion. Translational motion, gotta clear the area. Translational motion is relocating. No. Okay, gas particles have a lot of translational motion. Solid particles, not so much, are they? Okay. Oh, we'll try it.
What would happen if you reduced the item's atomic mass to zero?
If you what? Took something
Reduced
to...
an item's atomic mass to zero?
It would no longer be matter. Have you reduced it to zero? Because by definition, all matter has mass and occupies space. I don't know if that answers your question. But now this is along the lines of your question. One of the things I brought today, I think, is a thermometer from the lab. Or not. Yeah, there it is. Because I kind of wanted to get you thinking about thermometers. Okay. So this is just one of those where it's got liquid inside the bulb. Sorry. And basically, whatever you want to measure, you dip the bulb in. Okay. And so if I like wrap my hand around here, you know, I should probably see the liquid go up. So temperature. How do I say this? Temperature is an indication of how hot my hand is, but do you buy this? That my hand has a certain amount of thermal energy. My hand has a certain amount of thermal energy. Temperature is one part of how much thermal energy my hand has, but it's not the whole thing. Okay, actually, I think I have a slide that says the temperature of something, okay, is not the whole story, which how much thermal energy something has. They're related, but this is just saying how much. This actually, like the slide says, when I do this, this is saying how fast are my molecules of my skin going, and it's responding to it. Okay.
So basically, if you want to look at it like you would a volcano, the temperature of the caldera is so high, the thermal energy itself can blow the top off of it.
The thermal energy would be different than the temperature of the caldera. The thermal energy would go back to what is hot. I mean, is it the gases that are hot, or is it the liquid magma that's hot? I mean, temperature or thermal energy goes back to the object that is hot. Okay, not just what its temperature is. So you can have two objects at the same temperature, but they have different amounts of thermal energy.
Temperature is also controlled by pressure as well, though.
It could be a player. So this actually is kind of what we've been talking about, temperature versus heat. You can use, and I would encourage you to use heat and thermal energy like they're the same. Heat and thermal energy, how much heat an object has. And again, I'm kind of setting the stage for later on. We're going to talk more about heat and thermal energy. Okay. What's that?
heat is the energy possessed by an object due to the kinetic energy of motion at the time of atomic lever.
At the time of atomic, oh. What did I want to say there?
Level. At the atomic level?
Yeah, at the atomic level. At the small level, at the small level. Lever? Typo. And it didn't catch it on my spell checker.
Well, it's because it's still a word.
That's right. That just means little level. Okay. So,
Switch now?
what's that?
You flipping a switch now?
Maybe. So there are 3 ways you can get energy from point A to point B, if that's your goal. And in general, here they are. One is radiation, and you might think, well, Mrs. Snipes, you said EM radiation is something important with what the sun's sending us. And it's almost like the sun sends us electromagnetic radiation using radiation. So the example of radiation we have here, if you have a campfire and you're trying to boil water, okay, the example here of radiation is just that thermal energy, okay, going from your campfire. Yeah, radiating. Have you ever heard of infrared radiation? Okay, that's kind of what we got going on here. Infrared radiation, heat. Okay, heat is going in all directions, radiation. So also in this example, we have what's called convection. And convection actually is happening within the pot. You might have run into convection before when you talked about plate tectonics and kind of how the slabs of the Earth's crust move around, okay, using little convection cells. A good example of convection cell, even better than that, is a lava lamp. Okay, with the lava, they are cool. You turn them on, and basically they get hot at the bottom, and then that heats the fluid, and as that fluid heats, it expands, and it becomes buoyant or less dense, and it rises. And then after it rises, it cools, and as it cools, it falls. And then it will heat back up again. Okay, those are actually 2 convection cells. And in the case of the lava lamp, basically you are relocating heat from here to here. That's why it's a movement of thermal.
Convection oven.
A convection oven.
That's it.
Mm-hmm.
All
The convecting air, and actually all forced air, I guess heat, would be using convection.
Let's get an old school coffee pot.
What's that?
Old school coffee pot runs by the same theory.
Yeah, I can buy that.
An old school one. One of the pressure ones.
percolators.
Yeah, all percolators. So the last one is conduction, and conduction is the bump to bump to bump to bump. Conduction's kind of like if you play telephone, where you say something over here, and they kind of goes down the chain like that. Play telephone. It does get confusing. You're like, that's not what I said. But that reminds me of conduction. And in the Earth, an example here is what's going to happen after a while. And try to ignore this, his hand getting hot from the radiation. But what's going to happen after a while with this handle?
Heat's gonna transfer to the handle.
The heat's going to transfer, exactly, and that transfer is the conduction. Molecule to molecule to molecule to molecule within this handle. Actually coming up from the water in the pan itself, right? Yeah.
And when body being made of so much liquid, it doesn't naturally have a amount like
Yeah, I don't think that's a good thing. But here in weather, this is from the sun. Okay, basically the sun gets its energy by radiating it. Okay, but the other thing, and I'm going to show you an example here in a minute, is that we definitely have within the Earth's atmosphere blobs of air relocating, and as they relocate, they take their temperature with them. They can move their thermal energy from point A to point B. Mm-hmm. And then actually I have a little example here that we're going to look at more of a blob of air, okay, that relocates. So here's the deal. If it's a sunny day and you wear a dark colored shirt, you're going to be hot, exactly. And in this example, that's kind of what's being shown down here. You know, picture a deal where basically you have, this kind of look like plots, like farm fields or something. But for whatever reason, you have a different color down here that's different than the rest. Okay? So it's conceivable that like wearing a dark shirt, basically it's hotter than the surroundings. Okay? So what happens then is that air gets hotter than its surroundings, and what it wants to do is lift, kind of like a hot air balloon. I'm describing warm air going to relocate upwards. Why? Because, have you ever heard hot air rises? That's what's happening here. Okay, so you have a chunk of, and we're going to talk about cute little blobs of air that kind of do their own thing. Blobs of air relocating from the surface upward. All right. One of the things about blobs of air going up, we'll talk more about this, is two things. One is a blob of air that's going up actually will get bigger. And it's not entirely dissimilar from, remember I showed you that weather balloon? When it goes up, it gets bigger and bigger and bigger. That's actually why a parcel of air gets bigger and bigger and bigger. Now, we can't see the edges of the parcel of air, but it does. It gets bigger. The other thing is it cools down. And it can cool down to go ahead and for condensation to form. Remember, I've already told you when you see milky white clouds, water is it a liquid or gas?
Gas.
Liquid. If you see liquid, if you see clouds, it's water
Oh, right,
liquid.
right.
Yep, and it cools down to liquefy. So actually, that's what's happening here. And if something rises, something needs to replace it. So actually, you kind of see this looks like a lava lamp, right?
It happens quite often with large bodies of water.
Yeah, it definitely could happen around large bodies of water. Have you ever heard raptors, birds catching the thermals?
Mhm.
Okay, that's what they're doing.
There's like vultures, big birds that can't hold their own body weight up. They have to use
They're looking for that rising currents of air.
those small planes have to watch out for the thermal pockets. 'Cause they can
Small
cause
planes?
crazy
Mm-hmm.
things to happen.
It's definitely a player in the Earth's atmosphere. And more prevalent, obviously, on a sunny day. Okay. So, to me, and this is the first semester, I'm like, oh, really? So, to me, there's almost the verb radiation. The verb radiation. Verb means you're doing something. The verb radiation says, I'm going to get energy from here to there. Okay. There's also kind of the noun radiation. Electromagnetic radiation. Okay, affectionately called EM radiation. I was struggling with this poster this morning, and I finally gave up, but electromagnetic radiation comes from the sun. I've been talking about that, okay? And it has a lot of components. I call them cousins. I don't know if they kiss or not, but, okay. So this poster is about electromagnetic radiation. And you can see an assortment of energies that maybe before you took this class or never really considered how they are linked. They are all cousins, okay? They have similar, like cousins come from the same family and have similar characteristics, so also these do. Okay. One is that they all travel at the speed of light. Like, really? But if you look, light is, can you point there between the 0.4 and 5? Light, yeah. Light is right there. See that little segment? Okay, that's only one little segment of forms of energies we call electromagnetic radiation. The sun is sending all of this stuff to us. Okay,
Did you have some like
And-
AC current there as well?
what's that?
AC current?
Yeah, that's not in here, I don't think. Okay, that's actually kind of an electron thing flow. So that wouldn't be a form of electromagnetic radiation. But, oh, cute.
I was like, can I help you at the bottom of this maybe?
So what else we got? But they all travel through space. I'm gonna put it down for now. Thank you. I'll let you know. I appreciate that.
I was wondering
So-
about that because Tesla had developed the Tesla towers, which he was able to actually use to light bulbs in his hand from about a mile away.
Yeah, that's a different thing. That's actually using, I'm not familiar with that energy he used, but the reason light bulbs work is not as important here. What I'm curious about a light bulb is basically the light that's created. I'm not curious about how you make your light bulb work right now. But light bulbs are a good example of that visible light coming out. Do light bulbs ooze out heat, though?
Yeah.
Some of them do, depending upon how they work, right. Actually, if you look at the poster, or we're coming up here in a minute, thermal energy, which is sometimes called infrared radiation, that is a type of electromagnetic radiation. That's a cousin. Okay, so they propagate through in a vacuum at this what we call the speed of light, 186,000 miles per second. Okay, they have both an electrical and magnetic component. All these cousins I'm talking about. The extremes of the cousins, in a minute you're going to see gamma rays, electromagnetic radiation. Radio waves, electromagnetic radiation. They travel through space like this. They have a wave-like component to them, a property.
Probably oscillating or patterned, or they oscillate?
They do oscillate. They have and we're probably going to quickly get out of my realm, but they do definitely have a wave to them. And they have, and I'm not going to emphasize it much in here, but they also have a particulate part called photons. So they're particulates that are traveling in a wave-like form through space. I brought in, so when you buy glasses anymore, sunglasses, these are my sunglasses, okay? When you buy sunglasses anymore, they are polarized. And actually this goes to the wave-like property of them. The wave-like property of light that your sunglasses are trying to block. So here's the deal. They are polarized to get glare out. Okay, and I looked up glare before. I kind of chased this down one time. Glare is just kind of the random sort of, the sun hits, for instance, water. Have you ever tried to kind of look at, a river or something? And that glare just drives you nuts. So what sunglasses do basically are kind of put like, it's been described as like a picket fence. And they say, dude, light, you can get through my sunglasses, but you have to be going this direction. Otherwise, I mentioned glare. Glare comes from all sorts of directions. That's what's so bad about it.
Yeah. There's glare. A lot of water, and the light comes through the water, so it's glare.
Okay,
It's
yeah.
oscillational glare.
Yeah, very good. So, this kind of tones that down. But with this kind of picket fence comes some really kind of cool things, I think. So have you ever done this? If you have a pair of sunglasses that are broken, do this. Basically take it and do one over the other. The picket fences are going the same way. Okay, but if you rotate it, okay, basically you make those picket fences go perpendicular to each other. Okay, so there's no light getting through. We can continue and we make them go parallel to each other, perpendicular. Okay, these are polarized pieces of plastic, basically. Another thing about polarization is, have you ever been looking at your tablet before and you put on your glasses and you're like, dude, I have to hold my tablet just so? It's because your tablet is basically sending out polarized light, and your sunglasses are like saying, dude, I'm only going to let in this sort of orientation. So kind of play around with that. And actually, I can see how this works. See, with that, like that. Isn't that cool?
What's it called?
I know, it's the little things. Okay, but this is actually the picket fence, and this light is polarized. Okay? I know. So go break your favorite pair of glasses, sunglasses, and see what you got. So that was kind of a side. But this is even more important, though. So these cousins that vary from radio waves to gamma rays, I don't know about you, but gamma rays, bad, okay? Radio waves, okay, pass right through me. And they vary by how long their repeating unit is. I'm going to show you that, like, the radio waves, and some of you already know this, it's like, kilometers for a radio wave, one radio wave to complete a cycle. If you look at gamma rays, it's like a fraction, to complete one cycle. So one of the things you need to get under your belt for just this unit even is this concept of how long is that repeating unit? And of course, maybe not of course, but we call that a wavelength. Okay, how long is that repeating unit? I already told you radio waves really long. Gamma rays really short. Okay, and so you're going to hear me call this lambda. I think that's how you spell it. It's a Greek letter. So basically it's an upside down V with a tail. Okay, that's
Or an
wavelength.
upside down Y.
Or an upside down Y, pure upside down Y. I like that. Exactly. So if we call this A and this B, which one do you think is more representative of radio waves?
B.
B. Does that seem right? Longer waves? Exactly. So this is longer wavelength, be more like radio waves. Okay? And this is shorter wavelength, and it'd be like gamma rays. The shorter the wavelength, and this is important, even within these cousins, even though they're very similar, same forms of electromagnetic radiation, the shorter the wavelength has more energy. The longer the wavelength has less energy. Okay, so kind of busy there, but. So here we go. Here's different forms of electromagnetic radiation. Now, I don't do much with scientific notation in here. I don't do much with numbers at all. But as some of you guys already know, down here along the x-axis where it says 10 to the fourth, what number is that?
10,000. 100,000.
I'd have to do it this way. 1,
Yes, 10 by 10 by
1,
10.
2, 3, 4.
Yeah, 10,000.
10,000. Yes. Very good. So 10,000 meters. Okay. This one over here, whew,
10 to the negative 14.
okay, I'm going to put a decimal and 14 zeros.
Quadrillion.
Very small. Okay. That's the fraction of a meter this is. Okay, so let's see those energies. So now I told you that on your unit exam, you can bring a note card. I probably would put something like this on your note card. It's just worth a couple points, but maybe even more. I want you to know these kind of in order. So the shortest form of electromagnetic radiation, gamma. X-rays. Hard and soft I wouldn't worry too much about, but after X-rays, we are bumping up against visible light, and I get so excited here. Ultraviolet radiation. You cannot detect it with your eyes, but what color of light can you detect with your eyes that has that name in it? Purple. Violet. Very good. So these are three cousins. The fourth cousin would be visible light. And if you're like me, haven't you ever wondered, well, maybe you'll wonder more when you look at all these different forms of radiation, but what if our eyes were sensitive to ultraviolet? Or what if our eyes were sensitive to infrared?
You'd be like a bird.
It'd be strange, yes. Then after longer, less energetic than visible light, we have infrared. So what color of visible light kind of lines up with infrared? Red. Red, infrared, they bump up together. That's kind of nice. Then on the other side of infrared, we have microwaves. And then radio waves. So meet the family. Okay? And the sun's sending us all of this. And we're going to talk, especially on Wednesday, how just more than just visible light, but visible light gets through, but the other stuff doesn't get through, or especially the short energetic wavelengths. So just to kind of emphasize, over here we have most energetic. I'll put E for energetic. And over here we have least energetic. Did you get that? Okay. All right. So let's focus on that one cousin called visible light. So one of the things about it is you're going to want to know the components. I read this somewhere that, how did this go? That Newton did not want, he wanted the number 7 in his colors. So, I mean, to me, indigo, I'm not sure what indigo is, right? It's what?
It's like a dark blue.
It is kind of like a dark blue. So, but if you look at the 7 colors of visible light, there they are. I don't know if you've heard this before.
That
Yeah.
mnemonic device, yeah.
A mnemonic device, exactly. And then I had a student tell me this. It's like the first name of a guy, Roy, and his middle initials G, and his last name is Biv,
Yeah.
B-I-V.
Helps remember that. That's how I always remembered the rainbow. Like,
Yeah, and the rainbow lines up this way, exactly.
boy, it has to.
And it stands for red, orange, yellow, green, blue, indigo, and violet. And as it is, we of course have the longest upside down Y wavelength here for red, and over here for violet we have the shortest
The most visible colors.
of the visible colors. Yeah,
Fire, sky, blue.
that wire sky is blue. Here's a joke for you, and it doesn't have to do with that science. It's like, why are the skies blue? It's not Raleigh scattering. Why are the skies blue? It's a joke.
I didn't hear what you said.
We didn't even hear the joke.
Why are
hear
the
the
skies
punchline.
blue? Why are the skies blue? No. Okay, so you won't get this because it's dumb. It's so we know when to stop mowing. Yeah, I know. I got it from my husband. So sometimes his are good, sometimes they aren't so good. So see if you.
Let me make one. Make sure you make the cricket sound.
Okay. So see if you can see the Roy G. Biv in this pretty Roy G. Whoops. Biv. Something like that. Yeah. Well, this is a good place. We'll pick up here on Wednesday. There's a good chance that we'll get through chapter 2, I think, Wednesday.
Here I was hoping for Boston weather.
What's that?
Yeah, I was hoping for Boston weather.
I don't know.
I want that. Is that white light? Is that what that's
For
called?
this one or this
No,
one?
The next one. Yeah, white.
Yeah.
Well, this way was Boston weather. You save money in the refrigerator and freezer.
I already do that, but like.
What's that?
If it's Boston weather, you save money in your refrigerator and freezer.
Well, I think I'll pay for my refrigerator and freezer. Thank you.
I put my son out on our back porch.